Okay, so today's content is about, it's called the block diagram of AI, and the idea was that I would kind of introduce many different methods so that you can have a wide understanding that what kind of methods there are in AI. I'm not certain if I completely succeed on this, but at least we discuss many methods, and what is very important in all of these methods is how the knowledge is encoded in a form that computers can understand. And all this kind of knowledge representation starts already from Aristotle's syllogisms, that he had these kind of logical rules that that you know from previous courses, I suppose. And there are many ways how to represent that knowledge and how to use that, and we will discuss about that a little later. And that way to represent knowledge was kind of good according to those ancient kind of understanding of what knowledge is, and a little bit like and these understandings have been a little bit like developed currently, and we have more powerful methods of storing data. Of course, these are also important in certain cases. And it's actually we use of these syllogisms all every day in our discussions when we argument things with others. So they are really important, but for computers, we have more powerful ways at the moment.
Yep.
And then there is this what you can represent as logical rules can be also represented as a semantic network, which is a graph that you can see here on the bottom of the screen. And this is a little bit more rich way to describe knowledge. For example, this graph here shows that there is a bird called robin, punarinta in Finnish, and that has certain properties. So it is an instance of something that has red color in it, and this kind of rusty red color in it. And it's a subclass of birds, and bird is a subclass of animal, and they are also subclass of vertebrates. So that's selkärankaiset, and it has certain parts like wings. So this describes now many kinds of relationships between objects. This subclassing is kind of taxonomy. So there is a taxonomy of all kinds of animals or many kinds of other things as well. It can be presented here easily, but it can also have other ways. So you have different kind of properties, these balloons, and then you have connections between them, and the connections has a type. Therefore, this is a semantic network. It's not only a network of arrows and bubbles, but you have also the type of connection between each of these bubbles. That makes it semantic. And with this way, many kinds of information can be encoded. And when you have this kind of information encoded in a computer program, you can search the different things from it. For example, if you know that you have seen a bird that is red and rusty color, you can then from this graph find out that, okay, probably it was robin, or it was robin. There's no other choice because there is no other birds in this database. And then you know also that it was a bird, and it was an animal, and it was a vertebrate, and it has wings. So, and also if you see a bird that has wings, then from this database, it has to be robin because there is no other options for that here. But of course, in a larger network, there could be many other options. So, but then you would know that, okay, there is a list of birds. It must have been one of these. And then you have a list of colors, for example, and then you can, if you lock one of those colors, you can reduce the list of possible words. So many kind of inference or decision making or information search can be made from this kind of network. And then they became these object-oriented programming methods, and they had a certain notation of information as well, and that was shortly being used as representing data as well, and this was called logical frame representation of knowledge. So this is pretty much similar, and the semantic network, there is also objects or topics, and sorry. And then connections between them, and this connection can have types. So it is a semantic network, but it is also something more, because all of these topics can also have attributes. So it is more rich way to store information than this plain semantic network. So now you could imagine that that if you know some of these features, that it had 2 legs or and so on, then you could start searching from this database that what could it have been. Or if you know that it was a penguin, you can see that it has 2 legs, it cannot fly, and it's part of there is something wrong, but it's part of this subclass. And okay, I have not updated all these names, but anyway, you could see that what other information is connected to this certain certain thing that you are interested in. And this is then just a method of searching information from this kind of graph. And then if you talk more about logics, so let's take this example. This is actually that I believe that there is a web page called Luontoportti, some port to the nature, that is describing plenty of birds and plants and different kind of things of the nature. It's a really nice site. They have really nice pictures of birds and their voices and everything. So that's definitely worth looking if you are interested on nature. But it is and it has also a search engine, so that it helps you to recognize a bird, for example, if you have seen one, that you can describe its properties, and then this search engine tries to figure out what bird that was. And I have studied it a little bit, and I think I understand how it works. So it has probably this kind of structure. So there are certain kind of that knowledge encoded of different species. For example, a color, it can be white, black, red, blue, many kinds of things. And the wings can be dark or white, or size equals to crow, equals to sparrow. So is it small or big bird? How does it fly? Does it swim in the water? And based on this information, you can find which bird it was from this system. So for example, if we have certain kind of statements, that color is white, let's call it statement A, wings are dark, we call it statement B, size equals to crow, we call that statement C, circulates in the air is D, swims in the water is E, and then the final conclusion is that it was a seagull. Q is a seagull. So then we can, with propositional logic, we can formally describe it is in this form as a formula. So if A is true and B is true and C is true and D is true and E is true, then it implies Q. So we can kind of prove that Q is correct if all these A, B, C, D, and E are correct. So and it has a search engine that you can describe these A, B, C, D, and E, and then it defines, it tries to figure out what bird it was. And probably it is this information, how it is coded in this knowledge base of Luontoportti, it's probably written there in opposite way, because that's more convenient. So that they have selected a seagull Q, and then they have marked there that the seagulls are white. So Q implies A, and Q implies B, so that the seagulls are also their wings are dark, and they are about the size of the crow, and seagulls are about they circulate in the air, and they can also swim in the water. And then when you have stored these facts on the knowledge database, and then you have found that A, B, C, and D, and E are true, then you can imply Q. And there are certain kind of automated or algorithms how you can solve these kind of facts from a logical database, how you can prove a hypothesis. So that if your hypothesis is that this bird was seagull, how you can prove it. And one of the most common method is called resolution. You can click and see the details if you want. But let's just say that that you can store this information in the database in these kind of simple logical statements, and then you can search it using certain algorithms that are well known and well defined. And actually, you can also use a programming language. For example, the code example here is from Prolog. This was a programming language especially made for this kind of reasoning or inference. So you can here define certain kind of facts, and then you can query the database of new facts that can be the logical consequences of these facts. And there is a reasoning that you can do from the hypothesis to the if you, for example, have a hypothesis that this bird was a seagull, and then you want to prove it from this database, because you know that it was white, it has the dark wings, it has size equal to crow. You can do it in a program in two different ways. One is called forward chaining, and second one is called backward chaining. And in this forward chaining or prediction, that you take all these facts that you know, the properties of the bird that you noticed, and then you prove new facts from these. And one of these facts is that this bird, it was a seagull, and then you have proven it. So you kind of predict what are those birds that are possible based on these observations, and then you find the bird. And then there is also so-called backward chaining, which starts from the hypothesis that there were some observations of some bird. So let's try to find out if that bird was a seagull. And then you look at, okay, seagull has this kind of color, this kind of wings, it flies like this and it swims like this. And then you can either prove or disprove that this hypothesis was wrong. And sometimes the other way works better, sometimes the other way works better, but both are usable in this system. So there are methods how to search this. Okay, and then you can go and try this. Go to the Luontoportti and try to find this bird. And when you do this a little while, you notice that sometimes it works quite nicely, but there are some issues because some of these statements are not that. I think that they have tried to find out logical statements which are kind of separating these birds as well as possible. But still, it's a little bit kind of difficult to answer these questions. Were those wings dark or not? in seagulls. And also, if you just select one wrong kind of fact here to be true, then you cannot find the correct bird. Or what if there is like the young swan which is not white? Then this cannot find that either, because all these are like hard rules. If one is wrong, then everything will be wrong. And also it's difficult to encode the information of all possible birds in just pure logics. And remember last time we discussed about the knowledge presentation and axiomatic kind of AI. And this the idea in axiomatic AI was that you have a small number of axioms, and then you can deduce other truths or not truths based on that. And that could be kind of very widely applicable. But it was noticed that this is not very good. So instead you need to have plenty of knowledge, a knowledge-based system. But if you have already the number of birds is so large that it's a huge amount of work to encode all this information into this system. And therefore, it seems that this has to be very narrow AI, so it can only recognize certain number of birds which are encoded in this system. And it is not by means any sort of general intelligence. It's only a very narrow application area, only a search engine for birds. And still it is a hard work to do. So then could this be this encoding of information into the information system could be somehow automated? That's something we can discuss a little bit later. And also one problem with this system, but it was that everything was like true or false, so binary. So the bird has to have dark wings or white wings, but there is kind of nothing in between. Or you cannot say that I'm not certain, but I think it was black. So you cannot describe improbable or information that is not exactly certain. Uncertainties, you cannot express uncertainties in this kind of logic. So therefore, we can use probabilities to help us. And very simple kind of extension from these logical statements was that, for example, you could say that that if you have a seagull, that most of the seagulls have dark wings. So the probability that the seagull has dark wings is something like 70% or something like this. And then if you add uncertainties in these implications or the logical rules, then you can extend it to be applicable in a larger scale of problems. And this is exactly how the doctors have done, but that is not the best choice either. So let's think about what doctors are doing when they diagnose diseases. So there are let's, for example, think a case that a doctor has met a patient that has had that he thinks that perhaps the patient have had this DIA, that is how it is called. It's some sort of stroke. But it's only a kind of temporary, and it has so the problem in the brain blood circulation, and it has certain symptoms: one-sided face paralysis, difficulties to speak, one eye vision problems, nausea, double images in vision, difficulties to swallow. But not all patients have these all symptoms. And also these symptoms can exist for some other reasons as well. So how can you find out how these symptoms are related to this DIA hypothesis? And one can say that, for example, nausea is very common disease. It can be caused by many other conditions as well. So if this is so this is not very specific for DIA. So you cannot. So therefore, it is not very effective efficient of diagnosis purposes. But something like one-sided face paralysis, this is very specific to DIA, and not many other conditions can cause this. So therefore, this is the kind of primary symptoms that this doctor is looking for and examining. And if he finds these, then he or she can be quite confident that this maybe was a DIA. So apparently, it would be worthwhile to describe the connections of these symptoms to this hypothesis with some probabilistic methods. And that's what they do. I was wondering. I don't have examples of this. This is but you can think it is a similar way than this. That in a previous example, you had that if a bird is a seagull, it has white. It is white. So here in the same way, if the diagnosis is TIA, the patient have one-sided face paralysis at a certain probability, let's say 60%. And because there are not in many other diseases in their database which are also causing this one-sided face paralysis, they know that this is a very specific property for DIA. So that's why it's one of the most important ways of diagnosing it. What they do is that they have an implication. DIA implies one-sided paralysis at certain probability. So it is kind of softened logic. It's exactly the same structure than this logic, but it has probabilities in it. And this is actually how these käypähoitosuositukset, that is in English, it's kind of current care guidelines, that they are based on this kind of reasoning. And it has its benefits. It's of course much better than pure logic, and it's also like quite convenient to gather this kind of information. Still, it has been a huge work to collect all these kind of connections between diseases and symptoms, but they can do it kind of locally. So only think of one disease at a time, and then think that what are these paralysis, and then separately discuss that is this one-sided face paralysis also related to many other diseases, and they said, no, not so much. So okay, so this is a very specific for this, and then they can make their this kind of rule base. But the problem is that it has been proven that this kind of extension of logic is not a consistent way of doing collecting information or expressing information. So they have a large database of these kind of rules, but it's not kind of consistent. So they cannot kind of make it automated so that they would have a computer system that could use all these rules and have an automated kind of diagnosis engine, because there are problems with this representation. It may be that if you calculate a probability of certain disease, it should be of course between 0 and 100, and you may get that the probability is 150%, and these kind of issues can happen. Or maybe some diseases, the highest probability you can get is 60%. So that means that it is not consistent. But it works pretty well for humans, because humans cannot keep all the possible symptoms and all the possible diseases that in their mind at the same time. So this is quite convenient for humans. But that is also the problem, that if you go to the doctor and then you have some kind of rare disease, that does this doctor know about this disease, and can he kind of suspect that? But no system is perfect. But this is kind of this is made for human beings, and it has its deficiencies, but it has, of course, very useful in practice. And also the gathering of all this information is quite awkward. And again, it raises a question: can we somehow collect this automatically? And also there is very fast so-called combinatorial explosion. So if you have a system that you have in one level, you have two possibilities, and then you can go to two different directions, and then again do different directions, two different directions. But when you go a couple of steps further, you have a huge number of options. More than the number of options is rising faster than any polynomial. So it's kind of the number of options explode. So very easily you will have very complicated network and very large number of decisions and information needed for encoding this. Graphs, graphs are one powerful way of storing information that was already seen in these. These are also graphs. So nodes connected or vertices connected with edges. These balloons are called vertices, and these connections as edges in graph terminology. And with graph, you can encode many kinds of information in it. For example, maps. This could be like nodes or vertices could be like towns, and the edges between them, for example, roads. And then you could easily represent the knowledge of a map as a graph. And then, of course, these towns, they need to have also some other attributes like location, and these edges, perhaps the distance between the towns. And then you could use this to search a route from one town to another using this information. So this is what we will use also in the tools section to try different algorithms for navigating through a map. And also, like if you look at this graph, there are also only these edges, and they don't have arrows. So this is called a bidirectional graph. So you can kind of go through these edges in any direction you want, or both directions. So therefore, it's bidirectional. And then if you add arrows, that for some reason you only want to go through this edge in a certain direction, you put arrow there, and then you got a directed graph. And also, this graph has cycles. So if you go here, you can drive around this loop as many times as you want. But there are also graphs which are not cyclic, and those kind of graphs are called trees. Here is, for example, a cyclic undirected graph, and it can be expressed as the set of vertices, so these boxes, and the set of edges, which are the lines connecting these boxes from each other. It can have a root node or some other kind of information as well, but it is just a collection of vertices and edges. And this is a cyclic because you can go around certain cycles here, and it's also undirected because there are no arrows. And this, on the contrary, is a directed graph, but it has also cycles because you can go to the same node from two different routes. So this kind of forms a cycle as well. And then you can have an uncyclic graph. This is also directed, and all acyclic graphs can also, they are also called as trees, because you can always organize this as a tree. And in this case, you have the root here, and then you have different branches, and then you have here the last nodes here are called leaves. And this is a little bit funny tree because it has its roots, it is upside down, so the roots are here and the leaves are on the bottom, but this is quite often how they are drawn. But you can of course draw them in different way. But in this way, this is the root tree upside down, root is in the bottom and leaves are on the root is on the top and leaves are on the bottom. And this is actually, I think this is the same graph, or is it not? From 4 you have connections to 10, and there is no connection to 10. So these are different graphs. But this is also a tree, it has no cycles in it, and you can also rearrange it to look like this if you want, but it doesn't matter how it is organized. So then some example about using graphs for representing knowledge. And in this case, there is this is now some belief network. So this tries to describe our some kind of belief system between different nodes. For example, in this case, there is a what this network now describes is that if there is happening a burglary in some house, then at a certain probability, the alarm system will recognize that, and it will sound an alarm sound. And if the alarm sound is on, then at a certain probability, was it Mrs. Gibbons will hear it, and also at a certain probability, Dr. Watson hears it. So if some of these persons hears an alarm sound, at a certain probability, we can also conclude that there was an alarm on in this house, and at a certain probability, there was a burglary. And if this Mrs. Gibbons also heard this alarm sound, it kind of makes this hypothesis of burglary more probable. But if she didn't hear it, then it makes it less probable. And now, while we have encoded all this information in this belief system, we can calculate the probabilities of different hypotheses based on the observations that we have. And this is usually done using a Bayes rule and statistics. So we can describe these connections between the nodes as conditional probabilities. So BS bar B means that what is the probability of alarm sound in case of burglary. So that if burglary happened, what is the probability that this alarm sound is switched on? And probably those who are delivering these alarm systems, they can tell you that what is this probability, that this is very accurate alarm system, and in 90% of cases of burglary, it will notice it and ring an alarm sound. So then this would be 90%. And it can be also learned from the data. so that you can kind of study a large number of burglaries and calculate that how often this alarm was actually alarm system was working and how often not. Sometimes there was power outage, and sometimes the burglaries could able to switch it off and whatever. So then you can calculate that what was the probability or what is the probability of burglaries in this area in general, and what is the probability that how often this alarm sound was switched on when the burglary happened. That both happened, yes, that alarm system was switched on and there was a burglary. And you can calculate this, the number of cases of burglaries in this area and number of alarms while there was burglaries in this area, and calculate this probability as well. So then you know the probability related from the burglary to the sound. And but then, and this is exactly the same, that you can calculate also the opposite probability if you want. But what is interesting is that you can reverse this inference using the Bayes rule. That if you know that the probability of sound, alarm sound, in case of burglary is something, then you can also calculate that what is the probability of burglary if you heard if the alarm was on, by using this Bayes inversion rule. So, and it goes like this, so that I can calculate that conditional probability of burglary in case of sound by using the knowledge that we already have, that the probability of sound in case of burglary times the probability of burglary divided by the probability of this alarm sound. And that makes it possible to encode this information in one direction and then use it also in other direction. So, and because this Bayesian rule is here so important, this is called like Bayesian belief network. And now we don't directly imply that burglary always leads to alarm, and alarm always here leads to these observations. But we add certain probability in them. And if these are handled as probabilities, this is a consistent system. So it can be described a large amount of information in a consistent way, so that it is kind of certain that you will get the probabilities between 0 and 100%. And there are the difficulties with this belief network was that it was difficult to solve, but now there are efficient algorithms for solving these Bayesian networks, and it was actually in 90s they were really popular, and also in for example in Microsoft they made plenty of these kinds of implementations of Bayesian networks, and for example this paper clamp that they had and this kind of automated diagnostic methods that they had, they were based on Bayesian networks. And other difficulties is that it's actually quite hard to collect all this information and get reliable probabilities in all of these conditions. And then if you have a large network, you need a huge amount of probabilities, and then it's difficult to collect all this information in one place. And there are algorithms that you can learn this structure from data. So this needs to not to be made by hand, but then you probably need a huge amount of data. But so that's also kind of describing that it's difficult to know everything, to have an accurate knowledge about a complex network like this. So quite often it is so that our knowledge is insufficient. And so I don't know if you can say that this is this problem is from this method, or is it that the problem that it's difficult to know enough. In our everyday life, we may have a kind of overestimate understanding of our own knowledge, and therefore we can be quite certain on our own kind of decisions and opinions. But it also helps when you study these AI systems that it's not that easy to know everything, and you really need to know everything from this area if you want to have a complete decision-making system. Yeah, you can take a look at this further if you want, but there are kind of algorithms, and at least last year we had in the tools section, we trained some Bayesian network and used that as well. But they are maybe they are less common nowadays, so they have been replaced, or some other methods are quite more often used. Then we can study a little bit about yes. So in a similar way than there are kind of formal algorithms how you can solve these logical databases that you can prove statements either wrong or true. There are also algorithms how you can search these graphs through, and we will go through them more in the tools section. But then what has been missing here is actually that how to make the computer to learn these things. When we discussed about general AI and narrow AI, it was kind of so we noticed that for general AI would be able to solve, or a strong AI would be able to solve different kind of problems in different domains. But now already it becomes quite clear that if you want to be able to solve problems even in one domain, it already requires a huge amount of data. So these methods that we use currently, they are like these knowledge-based methods, and they require learning a huge amount of knowledge before they can work. So the general AI would need to know a huge amount of knowledge about everything, and therefore it seems like quite impossible. And especially if you would need to kind of try to manually create these knowledge bases, it would be quite difficult. But one approach of seeing machine learning could be that it can automate the learning of the data in the knowledge database. And let's take a look of machine learning from this viewpoint. For example, in this picture, we have two kind of properties or two features in X and Y direction. And then we have different objects. And some of them are distributed in this right bottom corner based on these features. So this first feature here is pretty large for them, and the second feature is quite small. Whereas these red dots are slightly in different corner, and the blues are here on the left side. So we have successfully find out some features which are capable of separating these objects pretty well, but not exactly. There are some overlapping here. So some of these blue dots are among green dots, and some of these red dots are among green dots. They can be also like that there is a mistake that somebody who has labeled these objects have put the wrong color in them, or it can be that these features are just not perfect, or there is a measurement error, or whatever, we don't know. But then we can create a decision rule that can be represented here like graphically like this, that this green line is now a decision rule which says that if we are on the bottom right side of this line, then these objects are green. And if we are here in this red area, which is surrounded by this border and this border, then it is this red object. And if we are in this area, this is a blue object. So clearly, this system that can make these decision borders has some information about this, knowledge about this domain. This could be, for example, diseases, and this system that can define these borders can now kind of make the diagnosis that these are certain disease, this is another, and this is a third one. And now the information is in a machine learning algorithm where these rules for drawing these borders is encoded. And this with machine learning algorithms, you can learn these rules based on the data, so that you must have some samples of these green dots and some samples of red and blue, and say that here are the greens, here are the reds, here are the blues. Learn how to make optimal decision rules for this, and then it creates some sort of decision rules, and the information is encoded in some data structure which is inherent for this decision making engine. And this is very simple case where you have only two features. This could be like two symptoms. This one-sided paralysis, for example, and then some other here, that how strong are the one-sided paralysis effect, and here some other symptom, and then you could separate these in three different categories. But in a real case, you can have, of course, more dimensions, but it's just difficult to describe or draw here. For example, you could have 100 different features, and then you would do the same in a 100-dimensional space, and you would draw these decision boundaries would be like hyperballs in 100-dimensional space. And this is no problem for this machine learning algorithms. Of course, the higher is the dimensionality, the more you need these samples to train the system. And this is one way of doing one kind of structure for making this kind of decision boundaries. This is trained for separating different soil types from satellite image. So it has certain nodes that if it takes first, in the first node, this has been using 13 different features. So this is a kind of 13-dimensional hyperspace where all these samples are. And these 13 features are different kind of colors from the spectral image. So normally you have an image which has 3 channels, but this has had 13 channels. But let's imagine that this is an RGB image. So we can say that, for example, at the first level, we have selected a blue color. And if there is blue more than a certain threshold, then we can conclude that this was water. But if there wasn't blue that much, Then we take the next color, for example, green. And if there is a large amount of green, then we think that, okay, this was forest. But if there was not that much green and it wasn't that much blue, so it was not water, not forest, then we go further and look, for example, the red and so on until we can divide these the pixels of every pixel of the image into a certain category. And then we can say that, yes, this is water, this is forest, this was hayfield, straw field, and dark soil. And actually, these decision boundaries have been made using decision trees, but there was plenty of them. It was called a random forest method. So there was a plenty of these small decision trees which created these decision boundaries. So this information related to these decision boundaries and to solving this problem was encoded in these nodes, which feature we compare and what is the threshold. So actually quite simple. And this created a tree graph that was then used for this decision-making process. And this training of this tree is completely automated. So you don't need to go and write this by yourself. But you can, and actually what is a good property of this tree is that you can draw it like this, and then you can understand how it works. So it is kind of a glass box that you can examine its properties, and you can even go and tune these parameters if you want. But it is already, the algorithm has probably already trained it to be optimal using certain criteria and the amount of data that you have. So if you change these thresholds and other properties, you make it less optimal. But of course, there can be many optimality criteria, but according to those that were selected during the training, this should be quite optimal. So this is one way of coding this information without much manual work. You just give samples and the algorithm learns, it creates a structure, it encodes this information, and then you can use it for to find, for example, the classes of these cases for unknown cases. But this can also be used for regression. So you can also not only select the class, but you can also kind of calculate the probability that how much this, how probable it is that this belongs to this class or this class or this class. And you can use the same mechanism for that. And this is just a simple example, only 2 dimensions here, only one tree, but there are much more sophisticated algorithms as well. Then also neural network is a way of encoding information on the domain for decision-making purposes. And the neural network is some kind of structure like this, that you have, like here we had 2 different features, 2 different diseases. And in this seagull case, there were much more properties. There were like color, wing color, how it flies, does it swim, and so on. So there can be many kind of input parameters which are fed into this network here from the left-hand side. And then the output nodes is that probability that it was a seagull, probability it was a crow, and actually there needs to be kind of all these bird species that we would like to recognize, or diseases if you want to recognize them. And then there are some middle layers here, which are only for, it is actually for encoding the decision-making information into this graph. And this is how this is used, is that you all again give some sample cases that when you have these observations, the bird is a seagull, and when you have these observations, then the bird is a crow. And then there are certain algorithms which trains the weights which are included in each of these edges. So each of these lines have some weight factor in it, and when you have a certain evidence, this evidence is used probably in all of these nodes, but they can have different weights. Here a small weight, here a large weight, here the middle weight, and here zero weight, for example. So these can use all this evidence here with different weights. And then this combines all these weights, calculates all these inputs together. So it's the evidence multiplied by the weight, and they are all summed together. And then there is certain kind of nonlinear excitation function that gives some output here, which is again some value. And again, here is the same mechanism, some weighting coefficient in each of these lines, and then these are summing them all together, and then there comes some output value. And so it works. And when during the training, these weights are all kind of optimal values for all these weights is searched, and optimal values for the thresholds here, and the excitation function is usually pre-selected, but the threshold for it is adjusted, and then it is kind of trained until it can predict the correct species. And then after training, this network contains the information about this domain in the form of these weights and the threshold values in these nodes. So this encodes the domain knowledge, and then you can start feeding in new observations, and it will predict the bird species. And this is this kind of structure would be very hard to train manually. So there is a but it is made for computer training. So you can train it by just feeding in plenty of observations of known species, and then it will learn to repeat that process. And because there are plenty of weights and plenty of parameters to learn, you need to have a pretty large amount of samples for teaching this kind of network. And if you have plenty of these output nodes, so plenty of classes, then you need even more. You may need more of these middle layers, and then you need more samples for training. And also, then after it has been trained, and then you can take a look at these coefficients and these threshold values, but they don't tell you much. So this is pretty much a black box, so that you don't know why it works, but it just seems to work. And sometimes this can be a disadvantage, and also a long training time, plenty of samples needed for training it can be a problem in some cases. But if you have plenty of data, this structure can learn very complex kind of decision rules. And this is now and these neural networks are those that are created this current boom of AI kind of things, because they can do so many complex decision-making processes. And even more complex. And speaking about these birds, there was a PhD thesis in Tampere University of Technology, where one researcher had a huge amount of bird pictures of birds, and he had taken all of those pictures, and he had also the name of all these birds, and then he trained a very complex neural network for recognizing these birds. The purpose for this work was that he wanted to study the birds that are flying nearby wind parks, so that if there are like those endangered birds, eagles or something, that they can switch off the wind turbines. And if there are just like seagulls that they don't care about them, so then no actions needed. Yeah, a couple of questions. I will answer them, discuss about them soon. So he created this very complex neural network for doing this kind of decision making. He could have used also this kind of neural network, but and indeed, if you put enough layers here, you can kind of, I suppose that you can train it to do arbitrary complex decisions, but then the amount of training needed would be so huge that you wouldn't find large enough amount of data for training it. And one more thing about these values here. So you have weights that are kind of, for example, the weights that are between the edges, for incoming edges for this node, they are something that this node has noticed that for making its predictions, some of these inputs are more important than others, and it has therefore adjusted this weight so that maybe this has very large weight, this has very small weight, and so on. But there is no kind of clear explanation what those weights are. They are not probabilities. They are just signifying the importance of different evidence for making the decisions that are necessary in this level. And similarly, when we go to the next level, this needs the inputs of certain middle layer nodes, and it adjusts the weights so that it can optimally reach its conclusions. And none of these conclusions are like in these middle layers are something that could be easily expressed as probabilities or something. It's maybe more that they want to kind of find optimal combination of features of these input parameters so that they can optimally separate different species from each other. So that these middle layers want to create decision boundaries which are optimally selecting different species, but are also kind of different from each other, so that there is maximum amount of information that is useful for making certain classification or regression on the next level. So this probably creates some decision boundaries which are different from each other and which are still effective, but they are not probabilities or anything. And also this to try to optimize the structure of neural network is maybe those who work more with them have some better methods, but quite often seems to be more like a trial and error and some rule of thumb that if you have if the problem seems to be very complex, then it is better to have more of these middle layers. But then if you need more middle layers, then you need more data for training. So I wouldn't say that there is kind of exact knowledge that how many layers are needed, middle layers are needed in which case. But then this convolutional neural network, this researcher has a very large database, a huge number of images, and also he had many species that he wanted to recognize. There was something like 10 different species, and he had hundreds of images about this bird species. So he used this approach that is very common nowadays, that is a so-called convolutional neural network. So he had here in as inputs, he had just a simply images of birds. That was normalized, scaled at a certain resolution, adjusted so that the birds was always in the middle, and maybe some the contrast and brightness could have been normalized. But these kind of normalized images were fed into this system, and then in this neural network, this convolutional neural network, you have two kinds of layers. Some of these are like making having calculations like these layers here, and some of them are doing so-called convolution, so filtering, and quite often low-pass filtering, so that you calculate the features based on this this input. So if you had here a certain kind of image like 100 and 100, 100 times 100, then you need to have 10,000 input nodes to read all those features, and then you calculate some amount of nodes on the next level, and then you calculate a convolution, usually low-pass filter, and then reduce the image size, and then repeat it again, and eventually you have a huge number of small images which are hopefully creating which are hopefully including important features of these original pictures. Those most important parts of the original pictures, which are resembling, which can be used for recognizing the species. And then again, in the end, there is a neural network and output nodes, which then describes how many of what is the probability of that this was a seagull and eagle and so on. And this seemed to work pretty well, and but it also needed a huge amount of data for training. Yeah, it would have been good if I would have in this material also a picture explaining this a little bit deeper. For example, what is convolution? I just take a look at if we had a very good example from here. Perhaps. Yeah. Yeah, there are like even nice animations about it, but I don't know if it makes this still so clear. But let's just think that it is a low-pass filtering. So if you, for example, have an image that is called 1000, that is the size is 1000 pixels times 1000 pixels, so 1 megapixel, and then you apply a low-pass filtering in it, the image will be like blurred, and then you will lose all those high frequency features, that there is no sharp edges any longer, and so on, and then you can kind of shrink the image to smaller and without losing information. So it's this kind of process that is going on in here. But you can also do in convolution, you can also run like for example edge detection filter, or you can high pass filter. And for example, edge detection could be sometimes useful, that you find the edges of objects in the image, and sometimes these edges can reveal the shape, and they can be therefore very useful for recognition of some objects in there. So some of these filters can be like low pass filtering, some can be edge detection filtering, and some of them can be high pass filtering or whatever. And these convolutions, you can think that they are like filters. And these what filters are used for these actual images are like learned during this process. So they are if this is the original input, and you can have here, for example, like 4 different filters. One can be low pass filter, one can be edge detection filter, one can be high pass filter, and some band pass filter, and also using different colors. And then you have 4 feature maps, and then they can be subsampled to smaller resolution, and the same thing repeated. Then you have again different filters, and they can use these already kind of enhanced features and find even better features, and then subsample them to a smaller resolution, and then put them in the neural network, which can use all these features that have now extracted for calculating the actual output. So something like this, it works. And making it is hierarchical like this makes it a little bit kind of less complex to learn. So it can handle kind of bigger images based on this information. And now the hypothesis is that this convolution subsampling chain here in the beginning is able to automatically extract the most important features from this original image. And then this neural network here in the end is kind of using these features extracted by this convolution subsampling part and makes this final decision. Because this feature engineering is a quite large work of any kind of machine learning application. So this is now a way to make it automatic. And this is a huge amount of calculations with all this filtering, and then you may need hundreds of images for training. So these are also usually running in the GPUs, so to make it much faster. So therefore also this neural network and convolutional neural network people want to buy those NVIDIA GPUs to be able to do this kind of calculation in a GPU that can be 100 times faster than running it in a CPU. But then you have, when you have trained this system, you have this domain knowledge now encoded as filter parameters in these convolutional steps. It's this subsampling can be probably hard-coded, and there is some number of layers, and then the information is encoded into weights and coefficients of this neural network part here, and then it can make decisions based on these images. And again, this is a rather hard process to train. You need plenty of example images to get this knowledge here, and therefore also people use a so-called transfer learning, that if you have, for example, teach this to recognize birds, that maybe this feature extraction and this network also contains some information that could be useful for recognizing cats from dogs, for example. And then you can try to take this pre-trained network and train it a little more for dogs and cats, and hope that it maybe can learn it faster than just the pure network from scratch. So this transfer learning has been quite important topic at the moment for trying to take this approach more practical. And this is also plenty of a black box method. So it's difficult to study how it works. However, you can look at these images here in the middle, and you can kind of understand better than how it what features it had extracted from these images, and maybe even tune them further. People are working also with so-called explainable AI, that they try to find methods to explain this trained network a little bit better. And again, if you think that this can be trained for a narrow application area, that you can recognize birds from images, but so it's clearly a narrow AI, weak AI, and if you would like to put this, if you would like to make this general AI, it would be, it's hard to imagine how that could be done. So therefore, the danger that we would accidentally create an AI that is more clever or more intelligent than the human being, I don't think that these are not yet making it. So it wouldn't happen accidentally. That we would reach the point that the AI is more intelligent than a human being, and then they would try starting to develop by themselves, and we couldn't stop them anymore to reach this kind of singularity. But I don't think that it's happening by accident, and these methods are not yet making it. Yeah, but explainable AI, unfortunately, not at the moment. Maybe then when we have this kind of tool section, we can talk a little bit more about that. And if you think about explainability, then this kind of tree models are kind of almost self-explanatory, so they can be easily explained. And also then these convolutional neural networks, you can take a look at its ingredients, and you can take a look at these images, and they can be studied, so you can learn more. But I don't know much methods for looking at this neural network, except that also that in the tool section we will try to teach this kind of neural network in an environment where we can actually see what is the consequences of these different nodes. So then you will learn more about this. So maybe I will also try to find more information about explainable AI there before we go there. And I also one more thing about this general intelligence, that nowadays maybe the biggest neural network available is called GPT-3, and it's a huge neural network, and it has been reading texts, and so they use a large amount of articles in the internet that it's reading, and it's kind of learning to write texts, and it can already kind of produce text that is hard to recognize from human author. And I have somewhere an example about the document that is written by neural network. I think it is also in the tools section, so we can discuss about that then later. But then there is a huge amount of text available in the internet, so no wonder that is the application area that they have selected, and it is then kind of already a more general intelligence in this text processing domain. but of course it is still a narrow application area. Yes, I don't know what else to talk now about these neural network issues. But then, if you look this area of AI in general, it's a huge. There are a huge number of algorithms, and nobody knows them all, I suppose. So you can take a look at it. There are plenty of things related to that we have already covered, and plenty of things that we haven't covered, and plenty of possibilities to learn more. So, but we will try to get some understanding of quite many issues related to AI and machine learning. Machine learning is a very important subset of AI and quite popularly used in these days.